What is the elegant connection of Nyquist's criterion to pole locations? Imagine trying to figure out if a control system will stay stable just by looking at its frequency response. It might sound tricky, but there's a neat way to do it. This is where Nyquist's criterion comes into play. It links the stability of a control system directly to where its open-loop poles are in the complex plane. The key idea is that the number of unstable poles, those in the right half of the complex plane, determines how the Nyquist plot wraps around a specific point in the complex plane. This point is called the critical point, which is at -1 + 0 in the real axis. The beauty of this connection is that it lets engineers check stability without solving complicated equations for the closed-loop poles. Let's start with the basics. In control systems, the stability depends on the location of poles in the complex plane. Poles in the left half-plane mean the system is stable, while poles in the right half-plane mean it is unstable. When we connect a controller to a plant, the combined system's stability depends on the roots of the characteristic equation, which is usually written as 1 plus the open-loop transfer function equals 0. The open-loop transfer function is the product of the system's transfer functions before closing the loop. Nyquist's criterion uses a principle from complex analysis called the argument principle. This principle relates how many zeros and poles a function has inside a certain contour to how many times the function's image encircles the origin. In control systems, the function we look at is 1 plus the open-loop transfer function. The Nyquist plot is a graph that shows the frequency response of the open-loop transfer function as the frequency sweeps from 0 to infinity and back. This plot is mapped onto the complex plane, giving us a visual way to analyze stability. The elegant part is how the number of encirclements of the critical point relates to the pole locations. The rule states that the number of clockwise encirclements of -1 in the Nyquist plot equals the number of open-loop poles in the right half-plane minus the number of closed-loop poles in the right half-plane. If the system is stable, meaning no closed-loop poles are in the right half-plane, then the Nyquist plot must encircle the critical point exactly as many times as there are unstable open-loop poles. So, if the open-loop system has no unstable poles, the Nyquist plot should not encircle the critical point at all for the system to be stable. But if there are unstable poles, the plot must wrap around the point at -1, a number of times equal to those unstable poles, in a counterclockwise direction to keep the closed-loop system stable. This makes the Nyquist plot a very powerful visual tool for stability analysis. In practice, this means engineers can look at the frequency response of the open-loop system and determine stability by counting how many times the plot encircles the critical point. This is especially useful when the system is complex, and calculating the closed-loop poles directly would be difficult or time-consuming. Handling special cases, like poles on the imaginary axis, involves slightly modifying the Nyquist contour to avoid crossing these poles. This ensures the analysis remains valid and accurate. The contour usually encircles the entire right half-plane, and the Nyquist plot maps this through the open-loop transfer function. To sum up, the connection between pole locations and Nyquist's criterion is all about how the number of unstable poles in the open-loop system determines how many times the Nyquist plot wraps around the critical point. This relationship allows engineers to assess stability quickly and visually, making it a fundamental part of control system analysis. It turns a potentially complex problem into a straightforward graphical check, saving time and effort while providing clear insights into system behavior.